Let's record. So I will just call this question maybe limit of integrals, right? Limit of integrals. And yeah, well, the question was limit n tend to infinity, integral from where to where? 2. Yeah, 0 to 2. 0 to 2, 2x minus x square to the power n, right? Yes. And we had to show that this quantity is 0, right? And so what was your reasoning? So, okay, first of all, how does this 2x minus x square look like? Right. Yeah, like this. And okay, yeah. Hmm. Yeah, that's right. And we are concerned with this portion between 0 and 2. And what is the maximum value? Always 1. Right. Right. Nagesh, good morning. Yeah. So we just started with this integration question. Okay. So yeah, you may have not covered integration on a rigorous level, but yeah, we'll just solve this problem. So just see what we can pick out of it. Okay. And yeah, so means obviously this. So what we are just trying to do is we are looking at this integration. Okay, this definite integral. So you forget this. But then you see this definite integral obviously depends on n, right? So for different values of n, you get different integrals, and we want to compute the limit. So it is just like a limit of sequences, but like you don't know the value of the sequence explicitly. So okay. So I mean, I planned to do this at the end, but since Nagesh was not here, so I said we'll just start this. Anyways, I think this will not be difficult, but let us see where the difficulty lies in this. Okay. All right, this. And then Aryan, what is after that? What happens after that? Hmm. Right. Yes. So right. So we can see that this. So this is the graph of 2x minus x square. But as we increase the value of n, so we take square, cube, and I mean it is obvious in a way that it that is what happens, right? Because for example, 2x minus x square, when you put x equal to 1 by 3, the value is something less than 1, right? So when that gets powered, that really decreases. But then there is a twist to it. It decreases, but like at x equal to 1, it always remains 1, right? So that's why it's the graph will always look like this, right? And it will keep coming down. Right? Yeah. So this vertical sort of strip will get narrower and narrower, and uh, and this horizontal thing will also get lower and lower. Okay. So obviously that means the area is 0. Okay. But how do we prove this? Why? Because there is a integration has a definition in terms of limits, and it has some properties you want to be which are derived from the definition. We have to use them to get to this. Yeah. So let's just think about this. Okay, you found a recurrence relation. Yeah, that is actually what you're supposed to do at, what is one of the things you're supposed to do at the high school level, right? Because this one has a recurrence relation. But just give me a minute. So yeah, Okay, so go ahead with the recurrence relation method. Okay, so this is maybe what we want to show. Yeah. So yeah, tell us how to. Mm-hmm. In is 0 to 2. Uh, okay, okay. Right. So you're rewriting it. Mhm. Okay. So why are you doing that? No, 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 no. So that is fine. But why can you do that? So you have to just say that x minus 1. Right. Okay. So that's why it makes sense to put it. And at high school level, this basically is a signal that you should put it. Okay. And then what happens? Then this becomes cos. Okay. After the d theta and everything. Okay. 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 Yeah. Sorry. So that's not correct. Okay. So can you just remind us of integration by parts separately? Okay. Ux. I just write it Ux Vx. Okay. Wait, what do you mean by integration of this? So, okay, let's just say, okay, let us first you say, yeah, this not be rigorous. Yeah. Yeah, certainly. But no, but just can we say it like this first? So we say like keep one of them fixed, take the antiderivative of the other, and then the integral of this whole thing. Right. And when you have these limits, then you just means loosely speaking, we just put the limits here a to b, and but here we will put the limits on this whole thing, right? Meaning that after you find this as a function of x, you put the limits. Okay. And then again same thing here. So this one probably is just a to b. But here when you compute, you don't put the limits. And obviously you should not. Right. So this is one piece. And then, okay, then tell me what recurrence do you get? Okay, do you remember the recurrence? Mm-hmm. Mm-hmm. I0 is 0. Okay. Um, some constant. Some it will be constant, but what way is it? 2. Yeah. I0 2. Right. Okay. So right. So Nagesh, tell us like which parts of this you don't follow so that we can work on that. Oh yeah, this recurrence even I don't know. Means this one is something that you will get when you do the integration by parts. Okay. So we will execute that, and you are fine with this integration by parts, right? This is the, and then obviously this. So it's a nice thing, but yeah, now I will suggest that we can take this for homework. Okay. We will try to prove this. So you have to take this as cos theta and cos theta to the power 2n, and take Vx as cos theta and then apply this. Okay, then you will find that is in minus 1 also shows up here. Okay, something. So, and one of the integrals becomes 0 or something, whatever. Okay. Or yeah, so that recurrence will come. And so this, and now from here it is very, very simple. So from here this will imply, and that also you have, it's like a homework, that the limit n tend to infinity is 0. Okay, because then we can basically solve for in terms of I0. Like if we just do this, so it's 2n minus 3 by 2n minus 2. It's a product in which everything is less than 1. So you try to prove that uh, the limit goes to 0. So this is actually a wonderful way to do, and this is how the problem is meant to be done. In fact, we are actually finding a formula for in, right? In terms of factorials. If you will simplify this, you will know what it is. Okay, so then this is done. Okay, but let us try to apply some method which will work uh, even when you cannot really compute, because then there is no analysis here, right? You're actually computing the thing, which is great. But if when you cannot compute, then there'll be trouble. So let me just give you my explanation, which is basically, which is more general, right? Because it won't be using the formula, but this intuitive thing which you have on the board, you have to just make that rigorous. So let's see how to make that rigorous. Yep. But before saying that, maybe um, I will need to say two things about integral, which I am sure you people will know, but just to abstractly mention them, because this is what we will use. So first thing is that if you are, um, yeah, that's right. It just follows. If you have, if you have this, right? So I'm not again, I'm not formally defining it, but whatever you know about it, it is sufficient. But just that to know this property from there. Obviously, it is very, very easy, but yeah, we have to this property. Okay, again. Oh, yes, of course, yeah. So that's C to B, this one property. And the other property which we will use about integral is that if suppose that if fx is less than or equal to some m, okay, for all x in some interval. Hmm, okay, then what does that imply? That implies that integral, because most of the integrals cannot be computed, we need to use properties to get talk about them. The only ones that can be computed is the ones that we do in till class 12 mostly. So C to D fx. So first of all notice that this will be less than mod fx, right? And why is that? Because fx is always less than or equal to mod fx, right? So mod fx is just it's the same function, but only that if f of x is suppose -1, but then mod fx will be 1. Takes the mod value of that. So you have f, then you apply the mod value. So obviously this is always true. And then if this is true, then this is also true. That is the thing about integral, right? That it maintains the monotonicity. That's the same thing about limits. That's the same thing about integrals. It's an increasing thing. Something it's increasing. So we have this, right? But then by the same thing, right? This will be less than integral c to d. And all this is very, very obvious, right? This. Just a constant function m, which is constant function on c to d. Yeah. And all this is just relying on that same fact, right? That integral is monotonic. That it is just relying on this fact that if hx is less than equal to gx, then the integral, obviously here you have to say some interval. There it's also same thing is maintained. And there is nothing in proving this. Right? It's very, very trivial. So obviously rigorous proof may need some work, but then what does this mean? This is just, we know how to do this. This is just d minus c. This is just a constant function, mm. If dx is just a symbol that we just keep using. It doesn't serve any logical purpose, but yeah, maybe psychological purpose. M is just a constant, and so you need to integrate that. That is a c, d minus c. So it is this. So we will be using these facts. These are very, very straightforward facts. But how will I be using this? Well, the idea to the way to do it is like this. That if you want to show that this is this, right? So what does this mean? Well, this means that so this means that what I will show, the limit is zero. Limit is zero means what? Limit is zero means that given any epsilon greater than zero, okay, it just means that you can make it arbitrarily close to zero. So given any epsilon greater than zero, I can find an n, right? There exists an n. So just to recall this, right? If you have a sequence of numbers, this is also sequence of numbers, right? Because these are actually numbers after you compute, but it's indirect. This is sequence. Now, what does it mean to say that limit an is zero? It means that given any epsilon greater than zero, there exists an n such that an, the distance of an from zero, so I'm not, there's no, is less than epsilon. For all n bigger than, for there exists an n naught such that for all n bigger than equal to n naught. This is what it means, right? This is just what it should mean, right? This is correct. This is what we will be using. So I just want to make the integral small. So let's forget about this for a minute. I just want this. So what does this translate to in our situation? There exists a n naught such that this integral 0 to 2. And this method, these kind of things are used all the time. So this thing is less than epsilon. I mean, everything is positive, so there is no need to put mod or anything, right? So this is what we want to do. Is that okay? Right? This is what we want. This is just a definition. I have, yeah, really not done anything. But yeah, one has to be very comfortable with these definitions. So then one can turn their intuition into the proofs, right? So this, and now we want to show this. So now this is what we will do. You know that given any horizontal line, right? Right? Given any horizontal line, uh, so let us call this some delta. You can make this, you can make n large enough, right? So that fx becomes less than delta. Okay, so let me say this again. So given any horizontal line there, so we want to say the area is small, right? So we want to use that horizontally, it goes lower and lower. So given any delta here, okay, and maybe this call is delta 1, okay, and given any other delta 2, which is close to 1, no matter how close to 1 it is, given any delta 2, right? One can find a suitable n, right? So that this quantity 2x minus x squared to the power n is, what should I say, is less than delta 1 for all x in 0 to delta 2. And of course, then there will be this thing, 0 to delta 2, and then 1 plus delta 2 to 2. Well, that is a symmetric, but still we'll write it. Is this clear? Because you cannot make it from 0 to 1, you cannot make it less than delta 1, because you can see that right in front. You cannot do that. But but if you want to an arbitrary degree of closeness to 1, then in that also you can do. You just cannot do it on the whole from 0 to 1. 1 to 2 is like not useful right now. It's a symmetric case. Okay, now this is clear, but can you prove this? Now this is just algebra. There is no calculus here. Can you just have to just find the n large enough so that this quantity becomes less than delta 1? Hmm. Yeah, you can still do that. That's right. But I'm not that is fine. That's a separate aspect, and maybe that is not necessary completely even for the exam. But conceptually, what you're saying, there is a slight problem. So the problem is that, okay, you are saying that given any given any a, you can find, which since a is less than 1, you can find the n large enough so that a to the power n is less than delta 1. Uh, but there is a problem, right? You need to you need to find the n that works for all values of x, right? You need to find the n which works for all values of x, and that is not possible actually. You have to restrict yourself to some delta 2, and you see the delta 2 did not appear in your argument at all, but it has to appear because you cannot do it. Hmm. Hmm. Uh, yes, but explanation? Hmm. Right. Hmm. That is fine. Yeah, it is less than 1, but it is not a fixed thing, right? You need to find the n which works for all x's. How do you argue that? Right. Yeah. So is this point clear to Nagesh, you also? This. Yes. So just to give an example, for example, if you take some n so that 1 by 3 minus 1 by 3 square to the power n is less than delta 1, that's fine. But then if I come up with 99 by 100, then that n may not work because the quantity grows. And this is where the difficulty lies, because we are not dealing with numbers anymore in that sense. We are dealing with functions, share collection of numbers. But the argument should be simple. Maybe the first time you're trying to do this, uniformly find n which works for all values of x. All values of x for some given delta 2. So you have to use the delta 2 in your argument. A hint is that this is an increasing function, which you know, but I'm just saying it in words. I mean, it's increasing between 0 and 1. This is probably the easiest way to say that. But yes, that recurrence way was the correct way to do the problem at high school. Yeah, that is very nice method. So, so it's an increasing function. Use that. So the delta 2 is fixed, and you need to say that to take some, there is an n such that, yeah, but everything in this, the value is less than delta 1. It is clear from the picture, but one has to just turn that into. Hmm. Okay, so you understand the question that the delta 2 is given to you, and for that you need to, and the delta 1 is also given to you. But your job is to make the value of the function less than delta 1 for all values between 0 and delta 2, right? So can you make it less than delta 1 for delta 2, for x equal to delta 2? Of course, that's what you have said, right? That delta 2 is less than 1, so you can find the n. So there is a n naught such that this is less than 1, less than delta. Can we do this or not? Because delta 2 is fixed. You have to, right. So one has to understand that delta 2 is fixed, delta 1 is fixed, and then you have to find the n, right? Which works for all x between 0 and delta 2. That has to be clear. This you can obviously do because delta 2 is a fixed number between 0 and 1. This output. But then that's it, right? But then it's an increasing function, right? So that implies that for all x in less than delta 2, also the same thing is true. Yeah, so it was right on the, yeah, it was right there. So this is nothing, it's just very easy. But yeah, knowing that it is increasing is necessary sort of in this kind of case, right? Otherwise, it's a bit of a problem. So this is kind of like uniform, uniform convergence, kind of uniformly going somewhere. So then we are done, right? So we have this. So I'm removing this. Now what should we do next? Now you have to split the integral. Now you have to split the integral. So this is clear. Okay, can you compute the integral? Can you estimate the integral now using what we have? But between 0 and delta 2. Right. Okay. So between 0 and delta 2, our function so is taken care of. Like it's sort of completely taken care. So I'm just forgetting 1 to 2 because this situation is symmetric. We forget that. So this thing will be less than what? This will be just 0 to delta 2, and this will be delta 1, and so this will just become delta 1 times delta 2, right? But then you have to show that integral from 0 to 1 is less than. So we forget the 2. So just 0 to 1. So what do you say? I mean, what do you have to say now for 0 to delta 2? Sorry, delta 2 to 1. I'm sorry. Yeah, this is less than delta 1 because delta 2 is less than 1. Or it is less than a constant. That's all we need. Now, delta 2 to 1, what should we do? Same thing, like what? Same thing we cannot apply because the value is not small there. It's not as small as you can make. Now in this you cannot really do anything. In this you cannot really do anything. If you do, then you have to again you'll end up in the same place where you are. Right. So how would you make the area small in that situation? Because the area depends on height, length, and breadth, right? So in this case, the length, sorry, in this case, you see the length is bounded. We cannot make it small as bounded, but we can make the base small as we want. Right. So you see, in this case, 1 exactly. So in this case, this thing is less than 1, so that's not presenting a problem. Okay. But yeah, you can make this. Now, because delta 1 and delta 2, so you see two things come in this kind of questions, right? So now, delta 2 was also in your hand, so you can make delta 2, to be just small enough. So, what would you do? You would say, okay, I will choose delta 1 to be maybe epsilon by 2, and 1 minus delta 2 to also be epsilon by 2, which means you had to choose delta 2 to be 1 minus. Those things you can work out later. And then everything just follows, right? And this is less than epsilon, this is less than epsilon, and so or epsilon by 2, and so the whole thing is less than 2 epsilon, which is what we wanted. And there is an n which does it, so that's it. So there is an n which does it, but then if you increase the n's, it will also work because it's a decreasing function. Sorry, no, it's a decreasing function. Oh, wait, there is a problem. Okay, so what do we do after this? So there is an n which does it. No, sorry, it's not a decreasing function. Okay, so we have proved this. Now what do we do after this? Yes, you add the inequalities and then we get this. Right. But then what do we do after that? We have to show that for all n bigger than n naught it works. I mean, we have found some n naught for which this works. We have found some n naught for which this works. But now if you increase the n naught, then what happens? You have to show it still works, right? Right. So this is a new point, right, Nagesh? This is a new point, right? We have shown that a n naught is less than epsilon. We have shown this, but we need to show that a n naught plus 1 is also less than epsilon. A n naught plus 2 is also less. Otherwise, it's not done, right? I mean, if you have a sequence, if you want to show it goes to 0, you have some term which goes to 0, but then one term goes up. Again, it goes up, again goes up, again goes. Then it doesn't converge. We don't call that converging to 0, right? So you need to show that for bigger n also it works. So you need to just, and this is actually trivial, so you should try to do this. So just show for this that this is also less than epsilon. Like, and for n naught plus 1, it is also less than epsilon. Okay, try to show that. Try to show that. Yeah, that is obviously enough. Yeah. Well, that is simply because that quantity is lesser, right? So this is obviously bigger than or equal to this. That is just because these are for all x. Obviously between 0 and 1. Yes, that's right. And this is it. This is true for all x in between 0 and 1. And even if someone is thinking that I'm like abusing the symmetry thing, no, because for between 1 and 2 also these numbers are again between 0 and 1, so same thing works. And in fact it's completely symmetric. So yeah. Anyway, then that's it. And if this is true, then this is true, right? Then this is true. And then this is less than epsilon. So fortunately we don't have anything to do there. So it's done. So it's an increasing function in x, but it's sort of decreasing in n. Right. It is decreasing in n, right? As n increases, it decreases. And so that is good for us. So all the things come and they solve the problem. Otherwise, yeah, it's difficult. Otherwise, it may not be true. That's the thing. Okay. So this is one of the things. I mean, obviously, this thing also follows from some very nice results. Okay, but they are a sort of a little beyond the scope. But let me try to say a few things. Okay, at least on so that you can use this. So you have understood this technique, right? It's a very nice technique where you see something that okay, in a certain portion it is that I can make the length, I can make the height of the function small, and then there is a certain portion in which I can make this small and it's bounded. So everything comes in play. Yeah, it's a bounded function. So right, okay. Yeah, yeah. What I really wanted to say is maybe I want to present this as something very. I want to present this as I mean this follows from something very very nice. And what is this nice thing? Well, the nice thing is this. So there is this limit, right? And there is this integral. That's the 0 and 1, right? And everybody knows when you just looks at it for a minute, they know and they draw the graph or whatnot. They know that the answer is 0, right? This is 0. But you see, this follows from what we have done. We have proved it. But you see, this also follows from something which is extremely desirable in mathematics. If suppose someone told you that you can exchange the limit and the integral, okay? If someone told you that you can exchange the limit and the integral, obviously, this can you do this or not without proof? If you can exchange it, then this happens. Now, this is you may say, okay, what is this? This is a function, and then it's a sequence of functions, and we are taking its limit, right? So it is like it's not a number in that way, right? but it is this, and then I mean, okay, so it's just function in it's sequence of functions, this, and so on. But then, and then you want to integrate this. So what's the natural way? I mean, you would have to just compute this limit for every x, right? For every x, you have to compute that limit. Is that right? That's the usual interpretation of this. So we have to make an interpretation here, right? Because here you did not have to make any interpretation. Here it is follows from your textbook definitions, right? That there is an integral, but that's a number, and so you're taking a limit of sequences, which is in our syllabus. But now it becomes a sequence of functions. But then if you want to integrate it later, you have to get a function. And so to get a function for every x, you have to find the limit. But then for every x between 0 and 1, what is the limit? It is 0, right? So this function that you get when you take this, I mean, accept the value 1 itself, right? What you get is that this thing is a function fx, right? Which we want to integrate. Okay. But this function fx is, what is this? This is just this function, which is 0, and then at 1 it is 1, this function, right? And you're probably told that you can ignore points while integrating, right? While doing Riemann integration, you can ignore a few points. That doesn't really matter. So you can ignore the boundary points, right? But in fact, if you see the proof why you can ignore boundary points, it is what I did earlier. It is that only, in a way. Yeah, if you want to do in Riemann language, set this. And so if you ignore that, right, then you're integrating the 0 function, so it is 0, right? So basically, this question is telling you that this question is telling you, this question is telling, saying, explain why you can exchange the limit and the integral. You understand, right? So the question is telling you, explain why you can exchange the limit and the integral. Otherwise, there's nothing to do after that, right? So it's about explaining why you can exchange the limit and the integral. So then that I'll just present as a general thing. So here we had sequence of functions which were given by powers. But let us now we just try to push ourselves a little bit and try to understand this, because this can be very, very useful, and you can easily prove it and use it in the exam. Okay, because the proof is not difficult, but it gives you a rigorous way to say why you can exchange limit. And most of the problems are that, because that's what the cheat codes are built on, right? That you can exchange the limit and the integral and do the problem non-rigorously. Right, suppose it's an MCQ, obviously, but sometimes you cannot, and then that's where you get caught. So that's why it's good to know that is it true from some result or not. So now suppose you have a sequence of functions. Okay, you can keep in mind the previous example. Okay, but suppose we have a sequence of functions and all their domains. So this is slightly more abstract than what things we have done so far, but try to understand this. So this you can take x to the power n also is an example or whatnot. The interval doesn't matter, but okay, let's check this. uh, right. Okay. So that is that. Now, suppose that you are interested in this. This is what our question was. Right? That for every n, you compute the integral. Obviously, this has to be definite. And then you get a sequence and take the limit of that sequence. But very often, we find ourselves wanting to exchange it. So I want a sufficient condition under which we can exchange this. Yes, I mean, yeah, monotonicity certainly is a very nice thing. Okay, and if you have monotonicity, yeah, that can help you, right? But the result I will be saying right now will not be based on monotonicity so much. Okay, but actually you are right. Monotonicity is the thing, but for that we have to go outside Riemann integration and go somewhere called Lebesgue integration, which is sort of a different way to integrate things, slightly different way to integrate things, but the answer it gives you is again that of Riemann integration. Okay, so that's the beautiful thing about it. But yes, so the problem with Riemann integration is that it, I mean, is that it partitions the interval on which it is. First of all, it's integrating over intervals, functions over intervals, which is a restriction. And then it partitions them into intervals and then tries to calculate the area. But if you see, that's not a natural way to calculate that's one way, but that's not the most natural way to calculate. So the point of it is that Riemann integration is unable to ignore points, is unable to ignore subsets of the interval which have area 0, and that's why it has the limitations there. Okay, but never mind. um, yeah, so this is the situation. Yeah. This is what we want to do. This is what we want a sufficient condition for this. Okay, so obviously if this has to be true, I mean, first of all, this limit has to exist, right? It means for every x, for every fixed x, you have to be able to take the limit. I'm not writing that, this is called pointwise convergence and so on, but for every x you have to be able to take the limit. Okay, now suppose that this limit is equal to fx, some function f. What do I mean by that? I'm saying that for every x you take the limit and then you collect outputs for every x, and that makes a function, right? And so that's I'm writing that function. Okay, this one is slightly you have to take care of, right? Slightly new business. But if this convergence is very nice, it's uniform. Obviously, all this is being said out of context, so it seems a little strange. But I think integration is this is a good place to see this, because you will see that it leads to something nice. If this convergence is uniform, meaning that for any epsilon, you can find the n. So given epsilon, you can find the n. You can find n naught such that for all n bigger than n naught, this happens for all x. I mean, this is what we were trying to do earlier, right? This fx was 0, right? This fx was 0, okay? So let us just make it 0 again. Actually, it doesn't matter. One can always translate. But just for simplicity, let us say that this limit is 0. But this limit is 0 in a strong way, meaning that given any epsilon, you can find the n, you can find the n naught such that for all n bigger than that n naught, and for all x, this is less than epsilon. If this happens, this is more than just converging. This is more than just saying that for every x naught, the fn values go to 0. It is more than just that. That's what we saw in the previous problem, right? You cannot find the n for every value of x. We had to restrict ourselves to some 0 to delta 2. We have to restrict ourselves to the 0 to delta 2 to say that you can make it less than epsilon. This much was not available to us even in the earlier problem, right? So this is a strong business. Can anybody give an example of such a case? Just a very quick example of such a sequence of functions. But the identity function does not go to 0, right? But you need a sequence of functions. So for example, if you take, and this will not work, that's why I'm saying, if you take fn x equal to x to the power n, same problem, it does not work, right? So you see, let's say we do 0 and 1, it doesn't work. You take this is fx equal to x, you take x square, you take x is cube, right? You get, but it doesn't work. So for this, again, the same problem, this is actually the same thing as the previous problem, right? You, for a given epsilon, you can find delta 2 such that you can make values for x between 0 and delta 2, you can make all the fx values small for large enough n, but for 0 to 1 it doesn't work, right? This example doesn't work. Can we give some other example which works. To give an example that works, right? Well, let's think. Yeah, one can always make examples, but some nice examples would be nice. Some interesting example, slightly interesting example. Yeah, examples are either non-examples or they are trivial examples, what I can think of. Yeah. Okay, then let me just give a trivial example, right? So for example, if you just take fnx equal to x by n, take this. From the graph also you can see that this will work, right? So between 0 and 1. So this is fx, this is f1x, right? f2x. Yeah, you understand, right? This falls like the broomstick, right? Falls. Yeah, and this will do this function. I mean, this function will have that property, right? Will have this property, right? So if you want this epsilon, then what should you take as your n? Just take so for example epsilon. Then just take a n which is bigger than 1 by epsilon, right? Then 1 by n is less than epsilon. Then x by n is less than epsilon, and it doesn't matter what x, right? So this is an example where x by n, which is the nth function, is less than epsilon for every value of x in the domain. Fine. We are pushing ourselves a little bit, but this should not be difficult. And even these questions are these uniform convergence questions are there without the language in, and I've seen it even in these entrance exams I'm talking about. Okay, so this uniformly converges, right? This sort of that kind of thing. Okay, so then there is no any doubt so far, but then we'll just prove this and finish. No, all right, then we'll move on. Okay, right. Now we're saying that if we have this, then it implies this thing. Okay. So in this case, it will imply that this is 0. So let's prove that. But it is trivial. Is there anything to prove? There is nothing to prove, right? Because this is already written here. Like fnx is less than epsilon for all n dot 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 dot, right? What we just integrate. That is because we have sort of exactly seen those things already. So we just integrate between 0 and 1. And that's it. That's what we wanted. And this is true for all n, and so there is nothing in this statement, right? So and now, but obviously the good thing is that now you can say if it is fx also and this is fx also, then also you can do, because then this limit is fx, this function is fx, right? And then you bring it to, you collect it, right? So this will become, so proving this is same as this. Fx doesn't have any limits. Its limit has already been taken. It is a limit. So you can do this, right? And then the question mark becomes whether this is 0 or not, right? If the limit was not 0, then you can just translate the problem and you come to this. You can take this function inside the limit because that doesn't have any n. It's already n is taken. It's already taken. Limit has been taken and that's the output. So you can push it inside the limit. And then you're asking, but this is again the same question. It all reduces to that question. Fnx, so you can take the function fnx minus x. This becomes the sequence of function, right? Gnx equal to fnx minus x, where limit is 0, it's uniform, blah, blah, blah. It again, same thing. Trivial. Okay, so this is one sufficient condition under which you can exchange the limit and the integral. Okay, but again, as we see, this was not useful in our previous problem, because actually there the convergence was not uniform. It was not like this, right? You could not find so we say in this case that fnx converges to fx uniformly, and you understand uniformly means uniformly without x is not playing a role. The function itself converges completely to fx. This facility was not available to us in the previous thing. Okay, right. So then what should we say? Yeah. So now so this is called exchange of limit and integrals under uniform convergence. Let me just end with saying just this small thing. Under this is called the dominated. Another more powerful way actually called dominated convergence theorem. Okay. So let me just mention this one, and I don't think I can prove it because to prove this, we will have to develop a new language of integration, which is basically motivated from probability, like expectation. And I mean, one can motivate it from probability. Okay, that was not, I'm not saying it was invented from probability or anything. Yeah. What does this mean? So again, we have a sequence of functions. Okay, now suppose you have a sequence of functions fx. Okay, and let's say that it is converging to a function fnx converging to fx, but this is pointwise. Pointwise mean that basically just for every point, you take a point and you just compute, right? For every point, you get a sequence of numbers, you take the limit, you get this f of x naught. And then take x1, take the limit under n, that is called that f of x1, that limit. So limits exist and it is pointwise like this. Okay. Let's say that this happens. So this is, and see, this is, so you agree this is a minimal requirement. If you don't even have this, then how can you talk about exchanging the limit? So this is a minimal requirement. There's nothing to remember here, right? If you ask that question whether I can exchange limit and integral, then this is a minimal requirement because you're going to compute the limit. So this is a minimal requirement. So under this necessary requirement, well, there is really nothing to ask. This, and the second is that if this is first hypothesis, I'm writing the hypothesis that this fnx is less than gx for all x, and gx is integrable. Okay, it's just for you people, for beginning, it is just that it is an integrate. It's function, that nice function that you can integrate, sine x or something that you can integrate. Okay, so gx is not the limit, but gx is sort of the savior, sort of. It's a dominated, so like everything is like it's an auxiliary function which helps you to understand the behavior of this. So if we have this, then yeah, then you notice that this actually implies that even for fx, it will be less than or equal to gx, right? Because it's a limit, right? Or if it's true, if this is true, it means that it is true for all x naught. Then you take the limit. Limit you can take, right, on inequalities. The inequality will be maintained, right? And so when you take the limit, you can push the limit inside the mod because mod is continuous, and then you will get that f of x naught is less than gx naught. And this happens for all x naught, so it's true for f also. So that's why it's not usually written in the hypothesis. All right, so these things are not difficult. So sometimes you have to say, check it for every x, because when it's pointwise, and earlier you did not have to check it for every x. So this is a thing, okay? Now this implies, and this is the nice thing, this implies that limit and this implies that you can exchange the limit and integral. This is the dominated condition. This is the dominated condition. This implies that limit fnx dx is equal to, you can put the limit inside and then take the limit, and we have already given that a name, so we'll call this fx. Yeah. Is the statement clear? No, g of x is just the auxiliary function. Yeah. Okay. Gfx plays a role while proving it. And in fact, when we prove it, we use some monotonicity things, or some positivity things, because gx will sort of make this, because we would like to, because these things, because integration is very easy to understand for positive functions. Okay, and the gx sort of makes the situation positive, because then we in fact consider the function gx minus fnx. Okay, So first we prove the theory for positive functions, all the easy results, hard results for positive functions. And then this gx serves as that kind of thing, that it makes a situation positive. Gx minus fnx we consider and we prove it, but then gx cancels because gx is gx everywhere. So, okay. So that is needed in the proof. You can understand that we have this. And now you see you can apply this to the previous problem, right? And because your sequence of functions was converging pointwise to fx, and what was the fx in our case? Fx was the function such that, it's 0 for x less than 1, it is 1 for x equal to 1. Not continuous. It is not a continuous function. And so it's not good in that way, but it is integrable. It's integrable. And what should you take as your gx? You can take anything. You can take actually fx itself in this case. Uh, no, no, no. You cannot. Sorry. You cannot take it to be fx. What can you take? You can just take gx to be the constant function 1. What else, right? And it's integrable, and then you can do it. Done. It is like okay. And in fact, more is true. This is not the old thing. In fact, this is true, and this is stronger. In fact, this is true. Yeah, in fact, this is true. Okay. And you from here you can prove this. You can try to prove this. Again, from the basic algebra, whatever we had. This is just from the properties of integral. You can prove this. You can kind of see that this is stronger. Right? Okay. So but the problem is that doing this, this in for doing this, we have to go to like a sort of necessary to go, because yeah, it is necessary in a certain rigorous sense to go to a different theory of integration called Lebesgue integration. But we cannot go there. There are some easy consequences of this. For example, some consequence which is called the MCT, monotone convergence theorem. There is another one which is called Fatu's lemma, but for that we have to introduce something called lim in for functions, which you may know or may not know. But problem is you will not. I don't expect you to be comfortable with that at the moment, even if I tell you. So yeah, lim in you may have seen, but I'm not sure if you're comfortable with that now. So we forget that. But in fact, that is the starting point for all these reasons. Okay, and that is another reason why we cannot say this. Monotone convergence theorem is what Aryan was sort of anticipating in a way. Is that if you have this, and this is a fundamental result. I mean, to work with areas, summations, double summations, actually everything is translated in terms of integrals. If you change your sense of dx, then integral becomes summation. Okay, and then you solve problems of summation using integral. They become better handled by that. So anyways, this is a sequence of monotonics. What do I mean? I mean for every x. I mean for every x. This happens. Then you can just close your eyes and exchange the limit with the integral. I mean, so okay, first of all, I should say this, right? So if these are monotonic, then obviously for every x limit exists. It may be infinite, but it exists. Okay, it exists or it is infinite. Let me be rigorous and say that. If it's a monotonic sequence, which means for every x this is growing like this, then obviously for every x is monotonic, it's a monotonic sequence, it will have a limit or it will be infinite. It will not oscillate. So fx exists. Now fx may obviously take the values infinite also, may take infinite values also. But then we allow that for a second. And then you can then you can do this. But that is basically this. You don't need anything else. You don't need function to be positive. You don't need anything. It's called monotone convergence theorem. You don't need it to be positive. You don't need it. Okay. But obviously, oh yeah. This also solves our problem. No, this does not solve our problem. So yeah, our thing was decreasing. Function was decreasing, right? Our functions were decreasing. Yeah. So yes, yeah. This is sort of increasing for in n, right? Yeah. Our function was decreasing in n, right? But you see, this has to be maybe bounded by something. Yeah, cannot be minus infinity. Okay, but you can apply it to our function also, right? You can just take our function was whatever fnx, and you can just apply, you can just consider the function 1 minus fnx for our function, initial function, right? Then 1 minus fnx, that becomes an increasing sequence of functions. For every x it is increasing, right? Because you're taking minus, just taking the 1. Why am I taking the 1? I don't need to take the 1. Yeah, just take this minus fnx, and this will do your work. This will do the job. Okay, right. In general, it does not work for certain reasons because it becomes minus infinity. We don't want, but our case is bounded, so there's no question of that. So you can just work with minus fnx, and then minus fnx limits you can exchange, but then a limit will be minus f, so you can cancel it and you can get. So even this solves our problem. This also solves our problem. Okay, and why do they solve our problems? Because this comes from a theory of integration where we learn to ignore um, points which are negligible, and Riemann integration doesn't ignore them, and that is the thing. Yeah, yeah, that is where the change happens while proving. Okay. Anyway, so we'll not go into all this. We will leave it at this. Okay. Yeah. So this is it. We will stop here, and we will not meet tomorrow. Okay. We will meet in the evening, but that's only for Nagesh and Shana. So Aryan, I will meet with you and Nagesh maybe next week. So sorry, I will not be able to meet tomorrow also. Okay. So this is it. Now you can just practice integration. So Aryan, from where are you solving these problems? Uh, CMI mock, yeah, yeah. So that's in general, that's a book, right? So you can just give the name